Hi. So we're going to talk about collision theory, and instead of which can go deeply mathematical. And so instead of me going through the derivation of where all this comes from, so I'm going to take a slightly different approach in introducing you to collision theory. And we're going to talk about things to consider from A and B coming together to yield some product. So we've already talked about that the reaction rate is equal to the rate constant times the concentration of A times the concentration of B, if the rate constant is some Kr in the forward direction. And this would be the observed rate constant. So you might have A plus B as some more, or yields products. This product might be some more complicated mechanism with 4 or 5, 2 or 3, however many reaction steps. And this Kr would then represent all of those possible reactions, and it would be the effective rate constant. Or it could just be simple, just second order, easy. Kr is times A and B, give you the rate. Okay, but what I want to talk about is that this reaction assumes A and B actually meet each other, so that you have some sort of connection between molecule A and molecule B. And not only do you have a connection, but you have all of these other aspects of physics and chemistry of that moment align and yield a product. So we're going to talk about the things that we need to consider that the likelihood of an encounter yields a product. So things to consider. That A and B encounter yields P. Okay, so number one, the rate of the collisions. And by the way, if we were doing this in person, this would be like the majority of the discussion. I would have y'all figure this out. But because we are virtual, I am just going to tell you. So pause me, try and come up with your own list, and then unpause me and get the answers. Or just watch the video, because likely you're not going to pause. But challenge yourself. Okay, so the rate of the collisions is important. The other thing is how many. So how fast this occurrence occurs, or not how fast, but the rate at which it occurs. Number two, the density of A and B, which is related to its concentrations. If you have a really, really, really high concentration of B, but a very, 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 very low concentration of A, the likelihood of B finding A probably pretty small. Or if you have really low concentrations of both, the likelihood of them finding each other very small. It will affect the likelihood of it going to products. Okay, next thing, 3, the energy of activation. So the activation energy, the amount of energy necessary to surmount the potential energy barrier, which we will get to in the next sections. But that we need to take into account. Number 4, the collision cross-section. So whether or not these things actually come together, and how likely that if they smash, do they smash like this? Do they smash head on? Do they smash, how, what do you call a smash, or how do you quantify a smash together? And then number 5, the orientation upon collision. So if A and B are coming together, do they come together like this, or do they come together like that? And depending on, like, if it's kind of the classic high five example. So when you high five, there's a point when you're going to high five someone and you kind of crappily do it and you miss, and you're like, that didn't count, and you got to do it again. It's the same idea. If they don't come together at the right way, it doesn't classify as a reaction, or it doesn't classify as a high five. Okay, 1, 2, 3, 4, 5. Each of these has a contribution to whether or not A plus B collide in a way that yield products. It also turns out that when you look at collision theory, which really is, anytime you hear the theory part, normally means there's an equation dictating that. Each of these becomes a factor in the general expression representing collision theory, specifically of the K value. So what we're going to do is I'm going to go through each one of these and kind of give you what the equation would be representing each contribution, and then we're going to pile them back all together to make the general expression for K. Cool. Okay, to connect to each of those independent things to consider, we're going to make the overall rate of the reaction equal to the rate of collision, multiply that by the number density, multiply that by the EA requirement, and then multiply that by the cross section, and then multiply that by the orientation. Okay, so what we're going to do, so the rate is equal to all of these things. And so what I'm going to do is I'm going to, again, break up the video into each of these, and we're going to fill in what the equation is underneath this main equation. So to start, so in your notes, if you're taking this, I would leave a space underneath this that you've written out so you can see where everything comes from. Okay, so the first one, so this is number one, the rate of collision. Okay, so the rate of collision is related to the speed at which A approaches B. So there's A, it's going to smash into B. This speed, and I'm going to use C because I believe that is what Atkins uses. If not, he's wrong. I think I'm 99% certain he uses C. Yes, cool. Okay, the other thing is you will likely want to jump back to section focus 1B. We skipped it when we were introduced to gas laws, but section 1B talks about kinetic molecular theory. In particular, if you have the number of molecules or particles versus kinetic energy, and I talked a little bit about this with reaction kinetics. So this distribution represents the kinetic energy, which is 1/2 mv squared. And so this velocity is going to be the velocity that we're talking about, the speed at which A hits B or approaches B. Now, there are a few different speeds. There is the mean speed, represented as C bar, and that's going to be not quite in the center of this maximum here. It's going to be about right here. So there's C bar. Then you're going to have C star, which is the most probable speed. And that's going to be the top of your peak. There's C star. And then you have down here, a little bit to the higher kinetic energy or higher velocity than C average, you have C relative. And this is the mean speed of A as it approaches B and vice versa. So the relative speed is as A approaches B or vice versa. So if you think about this as a relativity thing or a relative speed, so if I'm coming at you with a certain speed and you're coming at me with a certain speed, well, those speeds, it's going to be as if this one's, if you're saying constant or if you're staying still, I would be my speed plus your speed combined. And so that's why C relative is going to be a little bit higher than C average or C most probable. Okay, so taking into account these different speeds, and I should also add the mean speed. The reason that it's slightly off center is if we had a distribution that was nice and symmetrical, the mean speed and the most probable speed would be the same, but because temperature affects the fact that higher energy states are more likely to be filled than low energy states, thank you, entropy, you will have a slight asymmetry to this distribution curve, and that asymmetry favors higher energy, which means your average speed is going to be slightly higher than your most probable speed. Okay. So if you go back to focus 1B, you will find that C average is proportional to T over M 1/2. Woo! Where T is your temperature and M is your molar mass. Cool. Okay, so we're going to take this speed, which is proportional to the temperature and the molar mass, or inversely to the molar mass, radical that into this. So now we've got T over M 1/2 as the contribution of the rate of the collision. Cool. Okay, next up, we have number density. And so that's the concentrations of A and B. Well, that's cool because we know that the rate is equal to the rate constant times the concentrations of A and the concentration of B. So when taking that into account, well, there's that contribution. So we're just going to include for the number density, the concentration of A, the concentration of B. And for number 3, we've got the EA requirement, but we know that the rate constant, the EA requirement, and we know that the rate constant Kr has a temperature dependence that follows the Arrhenius law. That's cool. So what we can do is we can say that where this EA here is a proportion of the energy of activate, or the energy associated with the transition state, which would be when A is coming into B or colliding with B, there's a certain potential energy that must occur such that the activated complex can be reached. Now, in the subsequent videos, in like 2 videos from now, we're going to talk about transition state theory, and we'll dive deeper into what this EA actually represents. But you can think of it at the moment as a proportion of the total energy available in the system, such that if you have your kinetic molecular theory, which would be number of molecules versus kinetic energy, so there's some sort of EA here. It's a constant value, and so there's a certain proportion of particles that have an energy over that. And so depending on where your EA is, your distribution may be far above it or not far above it at all, which would dictate how many have a potential energy that they can then get to the activated complex and thus have a transition. So that then, this A e to the minus EA over RT goes right. And actually, I'm going to get rid of this A here. So we really just want this part because guess what's coming? So when we're looking at the rate constant, you can really lump a lot of this stuff in to A, and then you have it multiplied by the EA, or e to the minus EA over RT. So I'm going to omit this pre-exponential factor here in this representation. Okay. Cool. Pause. Okay, so now we're talking about the cross section, and this is represented as a sigma, and it's the region of a molecule that you can count as a hit. So I am going to draw figure 18A.1 to further demonstrate. Okay, so here I have molecule B represented as a sphere, and I have molecule A represented as a sphere, each of which has a diameter dB and dA. So this assumes that they're going to be coming together like this, okay, smashing into each other. And the question becomes, at what point does the connection between B and A occur that you can call it a hit? And so if we think about this as, so halfway between dA, so 1/2 dA plus 1/2 dB, that would be this distance. So if half of B is this far away from half of A, there's this distance, which I'm going to label D, which then can become, oops, draw this right, such that this D is now the radius of this area around B, okay? So that means that D is equal to 1/2 dA, the diameter of A, plus 1/2 the diameter of B, and this becomes the radius of region around B. Okay. So the area around B such that you can have a collision would be B is equal to, well, sorry, this would be sigma is equal to pi d squared, where this is the radius of this region. Okay, and don't be fooled. This d is not a diameter. Again, this is the radius, so you really should say this is pi r squared, where this is the radius of the region around B. Okay, cool. And just some examples. I'll write them on the board and then talk about them. Okay, so here I have argon, benzene, chlorine, and oxygen gas. And the cross section for argon is 0.36 nanometers squared, benzene 0.88, chlorine 0.93, and oxygen 0.4. So you can see that it varies quite a bit. And again, nanometers squared, this is an area. So pi r squared, and r here is the distance swooped out by half the radius or half the diameter of both A and B. Cool. The other thing that's interesting about sigma, the cross section, it is energy dependent. Of course it is. And so depending on the energy of each of these molecules, that will affect how large these diameters are. I know that sounds strange, but we're to the point now that we're taking into account all the stuff that you had no idea existed. Welcome to the beauty of the theories, where the closer you look, the more you see. So let's dive into the energy dependence of sigma. Okay, so the energy dependence of the cross-section, only the kinetic energy of a head-on collision is effective. And so if you have a coordinate system such that A and B are coming directly at each other, and remember the kinetic energy has a velocity component which has a direction within it. And so if they come in head-on, then that is going to yield an effective collision if your EA is high enough, which is a separate component here. But if it's not head on, so say A is coming in angled, so then what you'd want to do is you'd want to take the vector component of the head on collision component of the velocity vector. How do you do that? We won't, but you can. Check out figure 18A.2. Figure 18A.2, beautiful representation there. But what I can do is I can say that sigma of the energy is going to be equal to quantity 1 minus epsilon, and this is representing the energy of that non-head-on component, the energy of that component divided by the total energy multiplied by sigma, where you're going to have, and again, you'll have to look more into Atkins for the specifics, but you're seeing that there's some factor here that will, so 1 minus this component, EA will be smaller than E, so this will be a value that's less than 1. And so that means that there's going to be some percentage of the cross-section that is not contributing to the head-on collision. And if there's an offset here, so say you're actually here, then there's going to be some vector value here. Well, actually, I should have done that. So if this is the separation, then you can break this up into this component and this component. You're only going to be focusing on that component, which is a smaller contribution of the overall cross section, which means that this number is a smaller, so less than 1 value that will make your overall cross section slightly less. If, however, it's head on, this becomes 1. These two are equal to each other. And so, or actually it becomes 0. Well, hang on, how does that work? Well, it's such that the total cross section is then the cross section value. I think I might be missing a factor. Anyway, okay. So the other thing about cross sections is nothing. Okay, so let's add that on to our cross section value here. So that becomes sigma, knowing that sigma has within it information about the geometries of these molecules and potentially the energy contribution. Okay, next to orientation. Okay, go team. Sorry for the interruptions of the text messages. My sister just texted that she wants to knit my daughter a dinosaur hat. And I was like, well, can I have one too? Because why do toddlers only get to be dinosaurs? I want to be a dinosaur. Anyway, sorry, I digress. But I think this is funny now that I've added this to the video. whatever. Orientation, last one. Okay, so now we've got orientation. How do we take this into account? I am not kidding, with just an empirical factor called P. This is called the Steric factor. It is empirically determined. And it is a quantity that represents how much or how little steric effects cause a deviation from simple collision theory. I'm not kidding, I'll say that again. So this is a quantity that represents how much steric hindrance actually affects it. And again, it's determined empirically. And so you just take the number and you multiply it by everything. And I wouldn't get too caught up in it because there's debates about P. There's actually table, table, oh, no, not 18. Oh yeah, table 18A.1. You can see for a couple of reactions that P, it varies anywhere from 4.8 to 1.7 times 10 to the minus 6. P varies. Steric hindrance, steric effects of molecules sometimes matter a lot, sometimes matter a little. It depends on the reaction, it depends on the molecules, it depends on all sorts of things. And I think one of the beauties of collision theory is that you see that we know quite a bit about how these all come together, but there's still so much more we don't know when you add chemical character. When the reactions become specific to this type of molecule or that type of molecule, it becomes so much more challenging for us to come to a theory of everything, if you will, that quantifies exactly what will happen. Okay, so let's put all this together now and include so that we have the reaction rate, and I'm going to put is proportional to, because I don't want to put equals to, because each of these is, well, not that one, but each of these is kind of proportional to, because there might be an additional factor that you need, again, specific to that type of reaction. So this is proportional to T over M, 1/2 e to the minus EA over RT, cross section, times P multiplied by quantity, concentration A, B. And so this becomes your rate constant, such that we're left with the rate of the reaction is equal to Kr effective times concentration of A, concentration of B. And so this is the general form for the collision, taking into account collision theory. And you can see why now so many of us want to know, well, what's the rate constant? And you're like, it's just a number, who cares? It's so much more than a number. Look what you have access to if you know where to look. You can determine the energy of activation. You can determine steric hindrance effects. You can determine the cross section. You can understand things about the molar mass relationship, of how much does a molar mass affect the reaction rate. So much is contained within this K. And this is why it took Deanna a couple years to determine 2 K values for her research, because the reaction she was doing, the reactions she was trying to figure out were so complicated, and she had to have perfect conditions in order to detect them. You should go ask her about it. It's pretty cool. Okay, I think that's all I have, except for one quick side. Actually, I'm going to stop this video and I'll do a really short one on collision density next. Go team. Collision theory. Yay.